with this joy, let's assume then that the Earth is going that way. There's that fit what you want to see?
Yes.
Okay. And you are standing on the equator.
Yes, I am.
Whee! How fast are you going? You must have a tangential velocity at every instant. Now, I want to remind you, objects in orbit have to achieve a speed of about 4,000 meters per second to maintain a low Earth orbit. We calculated that a couple of weeks ago. Do you remember? If you don't remember the number, you know that we've calculated now things in orbit. And for an object in orbit, it's about 4,000. You're standing right on the equator, which means that you go around the Earth once every 24 hours. If I want to know your velocity, I would have to figure out how big a circle you make and how long it takes for you to make that circle. Nothing new here. So that would be 2 pi times 6.38 times 10 to the 6th divided by 24 times 3,600. I mean, I don't want it in meters per hour. I'd prefer it in meters per second. Wouldn't you agree? So thus, the 3,600 is to convert the hours to seconds. So please do so. Tell me how fast we're moving this moment if we were on the equator. I'm patient, but I think I know that some of you are going to get it. But I don't want to wait for all the button calculating. What's the number? Yes, sir?
Actually, I got 7,904.
You might have made a mistake. Yes, ma'am?
I got 463.96.
That's it, 464. 464 meters per second. Now, again, with everything else, is that a big number? Big is relative, isn't it? The idea of how big this number is kind of relative. It's not big when compared to how fast you have to go to be in orbit, but that's really fast. This is still faster than how fast pistols shoot bullets, which is usually somewhere just past the speed of sound, which is about 330 meters per second. This is faster than the speed of sound. I want you to understand that we are moving fast enough to create a shock wave if we were passing through air. Because things that break the speed of sound create a shock wave. We are traveling faster than sound would travel through the actual air that surrounds the Earth. Now, you might not appreciate that, but do you see why we get hurricanes? We are stirring the air with every mountain that travels through the atmosphere. Every mountain top is moving at hundreds of meters per second. All of them. That's why there's an amazing jet stream that propels the atmosphere around the Earth. What should amaze you is the direction the jet stream goes, because it goes in the direction we're moving, which means the air is actually moving slightly faster than this. It's bizarre. Just bizarre. Now, this is also why we fire rockets off at Cape Canaveral. They get a boost to their speed. If you need to accelerate something from 0 to 4,000 meters per second, it's going to take a lot of fuel. If you can cut 400 meters per second off of what you need to do, you can cut out 10% of the fuel, right? We're already starting 10% of the way there. Doesn't sound like much, but if you're having to carry hundreds of tons and you can save 10%, you'd save 10%, wouldn't you? So we launch things as close to the equator as possible. We've actually tried to float launch pads in the water farther south to get closer to the equator for the added benefit. Now, we don't launch from Texas because we don't want it to crash on Florida. We launch in Florida because you can crash into the ocean. We have a lot of ocean for crash space. All right, now the next question. And this is something that will be lost on a lot of you if you're not always paying attention, and this is worth paying attention to. The only way you travel in a circular path is if there's an unbalanced force acting on you. I've said that often enough where that really needs to be on your notes. I had a parent ask the other night about, how to do better with your notes. Start rewriting them. It'll help. But one of the things you should probably get internalized is you only travel in a curved path if there's an unbalanced force acting on you. Are you traveling in a curved path if you stand on the equator? You have to, right? By necessity, it's a curve. And none of the other rules we have change. Meaning, is gravity acting on you when you're standing on the earth? Sure. So there must be a force downwards. Are you in contact with the surface? If so, there's got to be a normal force. So if this is our free body diagram, the normal force will have to be less than the weight. There needs to be an unbalanced force. So mg minus normal has to equal ma. It's not 0. That means that if you stand on a scale at the equator, it will show you a weight that is less than your actual weight. Remember, a scale only reports the normal force. So if you stand on a scale, it's not going to report your actual gravity. And this is because as the earth is spinning, it's trying to fling you off of it. Right? So there has to be an unbalanced force to keep you on it. Ideally, we could rework this problem and see how fast you'd have to spin the earth to fling people off. I think some people should go. Yeah. Anybody who uses an iPad camera should be flung off the earth. I agree. Now, all jokes aside, if you walk something from the equator to the North Pole, because you're only going to be able to do it for a little while longer before there is no land at the North Pole, but if you walk something from the equator to the North Pole, it gets heavier. Technically, it should, because at the North Pole, you're not spinning anymore. You're just you're not going in a circle. You're just kind of going in a circle. You're doing this, right, at the North Pole. So technically, you don't need an unbalanced force for that. Your normal force would go up a little bit because the net force on you at the North Pole would be 0, while the net force at the equator would be a little bit. So I asked you to calculate, I think, the centripetal force or the centripetal acceleration. I don't remember which. It's not very big. It's this 464 meters per second squared divided by, you still have to use the massive radius of the Earth. And my understanding is that when you work this out, you get a really small acceleration. So it's not like it's a lot different. But believe it or not, that's measurable. Like that scale I have in the back of the room, it's sensitive enough to measure this difference. So between here and the North Pole, you could measure this difference. And the Coriolis effect and all of those kinds of things are all related to the spinning of the Earth. So, one with the two objects. Look, you're going to have to get to do this. And I recommend you start internalizing a couple of things. It is not a surprise that I'm going to use this relationship here, so I don't think I'm making sure you understand that. But it doesn't have to be this one. You should also remember that the acceleration of gravity on a planet is this. This is another favorite for this kind of problem. And you should know how to go from here to here. It was part of the FRQ for homework the night before last. And so I would strongly encourage you to know this because it's what makes up a lot of multiple choice questions. And it just comes from setting this equal to ma. That's all it comes from. If you're standing on a planet, this would have to be the acceleration of gravity on that planet. However, this problem is specifically about the force of attraction between two objects, and the only force we know about that causes an attraction like this is the gravitational force. I shouldn't have to tell you that it's the force of gravity. We've talked about all the forces in here that reasonably act on a system. So if you have two objects, they all are experiencing a mutual force of gravity. So I don't have to state that it's the force of gravity pulling them together. Does everybody understand? This problem tells you that they are experiencing 10 newtons of force when they are a distance, is it 1 meter? Apart. I wish I had not used 1 meter in the problem. Okay, I wish I had not. And you'll see why in a minute, but I wish I had not. I then say, how far would you have to place them so that the force diminishes to 2 meters? So would that mean bringing them closer together or farther apart? I would like more strength to that answer. And those of you guys who don't know the answer, understand you are staring at a 50% on Tuesday. Okay? Because that shouldn't be the hard one. R is the separation distance. It's in the denominator. If I want to make the force smaller, I need to make R bigger. They need to be farther apart. I want to diminish to 2 newtons. All right. I want to show you how this is done. And I've shown you how this is done once before. Please help yourself here and give yourself information. Start with what you know. Use an equation and populate it with what you know. There will be things you don't know, and that's okay. So pick an equation and populate it with what you know. I know the force is 10 newtons when object 1, object 2 are placed 1 meter apart. Now, I'm going to show you 2 ways to do this problem. A way I've never shown anybody in this class before, and the way I want you to do this problem. The way I want you to do this problem is to consider the new situation that is at hand, which says that when M1 and M2 are placed this new distance apart, they experience 2 newtons. I don't know what this new distance is, but it's probably some multiple of the original distance. Now, we did this similarly before. In the other examples of this problem that you've had, I've told you by how much a variable changed. So if I said you doubled the distance, you would have put a 2 where the C is. Does that make sense? You guys remember doing that? This problem is no different. But instead of telling you how much the one variable changed, I'm asking how much it has to change to make a specific difference in the force. The problem can still be done the same way. I want to find out by how much the distance has to change. So I'm solving for C. Now, to do so, what I need to do is I need to get all the things together that match the original. I want to move all of those things to this side and all of everything that's left to that side. Now, what that means is I'm going to look at everything here in the top. I'm going to push it to the right some. And I'm going to take anything that has been changed, like if I doubled the mass or doubled both masses or something, and move it to the left. But I didn't change anything on top, so I'm going to bring an explicit 1, just so I have a placeholder on the other side. On the bottom, I see C times 1, quantity squared. Well, I'm going to put the 1 part over here, because that goes with the 1 that was over there. And the C part, I'm going to put over here. And yeah, they're multiplied together. I'm just spreading them out some. This still equals 2. What I should have when I'm done here is everything that I had in the original, which I know equals 10. So I will replace now the original with the 10 that was in the original formula. When I do that, I can solve this for C. And when I do, I get the square root of 5. Please be careful. The square root of 5 is not the answer. The square root of 5 is the multiple. It's by how much we changed the distance. Right? You see, we multiplied our distance by C. So if you want to find out what the new distance is, you have to multiply the multiple times the original distance. Now, I know the original distance was 1, and you're going to get back to square root of 5. I know that. I told you from the beginning I should have made the distance 2, just so you'd be forced to do this extra step. But I want you to just know and have it in your notes that what you get there is the multiple. You'll have to multiply it times the original distance. And I didn't have to choose distance. I could have used the mass or something like that. But how much would I have to change the mass to get the force to diminish? All right. Some of you do not like this method, and you have expressed that to me a couple times now. So here's method number 2. Method number 2 is just as effective. In these, you will always get some collection of constants that you don't know. A group of things that aren't going to change. We know the distance is changing, but that means everything else is staying the same. Solve for everything else. Work it out till you get a value. Now, set up your new situation. Replace the group of constants with what you solved for. Solve for your unknown. This one is sometimes harder to employ, but it's an alternative. So consider the problem I gave you for homework that nobody asked about. One like this, where I ask what change would produce this value. Expect one of each. One of them is harder than the other, I get it, and that's okay. You'll do okay. Can I answer another question? In the time that remains, we have 10 minutes or so. Yes, sir?
For number 12, is an answer kinetic friction?
Can you tell?
Which friction force would be the same value regardless of how fast an object is traveling?
Yes.
Okay.
And folks, that's, please understand something. Kinetic friction is going to act on any object that's sliding, unless it's on a frictionless surface. It doesn't matter how fast you're going. The kinetic friction will be the same size force. So whether you're barely moving or zooming around at 400 meters per second, you'd experience the same kinetic friction. Friction is the only value that actually really changes based on your velocity. Let me say that different. friction is the only value that has a different function for when you're moving than for when you're not. Once moving, though, the kinetic frictional force is the same for all types of motion, any speed of motion. But the moment you stop, a different kind of friction takes over completely. Okay? I didn't have to write anything down for that. So, why is it a greater force? Is that also part of the question? Or do you just want to know the answer?
That's my question.
Okay. So here's the deal. Static friction is an inequality because it's called starting friction, which means if you have an object just sitting on the ground and you give it a little push, if there's static friction, it will apply a force to the object to keep it from moving. And if you push a little harder, well, then friction will get bigger to keep it from moving. That will continue to happen until you reach the threshold, the equality. That will be the maximum force it could apply. You push a little harder than that and you'll break the static friction. Kinetic friction will take over, which is usually less than static friction, and your object will begin to slide. That's what's called starting friction. Now, your question, which is why is static friction greater than kinetic friction, generally has to do with a couple of things. There's a couple of things happening at once. And remember, friction itself, this isn't a law. This is just what happens. It's how friction kind of works. But it's not really a law. Friction is inconsistent. And it's, two surfaces, two of you in the room can measure the coefficient of friction of the same two surfaces and get slightly different answers. Because there's little variations. Friction is caused by attractive forces between molecules at the molecular level. But it's also caused because at the molecular level, things aren't necessarily smooth. They're, little micro bumps everywhere. So sometimes little micro bumps fit together and sometimes they don't. So that's why it can be inconsistent. The reason why static friction tends to be stronger than kinetic friction is if they're stopped, there's an opportunity for van der Waals forces to also kind of come into play and stick atoms together some. And there's also things like cohesion and adhesion. Do you guys remember those words from chemistry? When you get cohesion and adhesion that occurs, at the molecular level, all of those tend to add up to make static friction. And once you break that, well, the atoms are still trying to be in contact, but you have created an artificial gap or a bit more of a gap between them. Those forces don't have a chance to set up, and that's why kinetic friction tends to be less. Is a kilogram meter per second squared. Now, I've brought this up a couple times. I'm going to kind of beat this horse a little bit. Velocity is meters per second. Acceleration is meters per second per second. These are both called rates. Anything with time in the denominator is a rate, meaning it's how fast something changes. All rates are like this. The interest rate, how fast your money changes. Right? Anything that's a rate has seconds in the denominator. Now, velocity is how fast your location changes. Acceleration is how fast your speed changes. If you look at Newton's law could be written as a rate. I could take one of these seconds and put it underneath the other one. And if I did that, I would get kilograms, meters per second over seconds. And I've now written it as a rate. Do you guys understand what I just did? It's algebraically the same. I took one of the seconds and put it in a lower part of the fraction. This is numerically okay. So algebra will agree with me. But what I have up here is the unit of another type of measure we've never studied, called momentum. Something we will be studying first week before Thanksgiving and right after we get back. Now, momentum itself is its own thing. I'm not going to talk about what it is. But buried inside the unit for the force appears to be a rate. This would have to be the rate at which your momentum changes, because this is the unit of momentum. Now, the reason I want to bring this up is because Newton's laws were actually never about mass and acceleration. Newton's laws were originally about the rate of change of momentum. That's how Newton actually formulated it. The problem with the way we learn it is that we suggest mass tends to stay the same as you push on objects. But that's really not what happens in nature. Look, your car gets lighter as you drive it, right? Because you're burning gas, expelling gas into the atmosphere. But you're burning gasoline at the same time, so your gas tank is getting lighter. You are getting lighter as you consume food and expel waste. Rockets consume 92% of their mass in about 11 minutes. It would be nice to have a way of dealing with that. Momentum lets us deal with things where the mass isn't always the same. And so understanding that means that you can deal with rocket science. So Newton understood this. Newton had a better vision, I think, than what we're doing right now. And he expressed force as the change of momentum over time. And if you compare these two cases and assume the velocity is the same, then the weight has to be the same in both of these. It's the same car. But in order for the system to curve downwards, there has to be an unbalanced force downwards, so the normal force has to be less. In order for the car to curve upwards, the unbalanced force has to be upwards, and so the normal force has to be greater. You do see that that plays out like a great multiple choice question, right?
Yeah.
The moon has 1/10 the mass of the Earth and 1/4 the radius. What's the acceleration of gravity on the moon? You guys remember this question? So the acceleration of gravity on the Earth is the mass of the Earth, g, over radius of the Earth squared. And this equals 10. We all okay? 1/10 of the mass of the Earth times g over 0.25 times the radius of the Earth squared. If I want to figure out the acceleration of the acceleration of gravity on the moon, I will need to collect the terms that look like this. So I'll move the 0.1 away from the me times g on the top. I'll move the 0.25 away from the re squared on the other side. I'll again notice I have all of that. So I'll get 0.1 divided by 0.25 squared times 10. Okay. I've done the problem a couple times now. You're going to need to do this on your next test. You should assume there'll be one like this, where I change parameters and ask what the new value is, as it does to come down. Again, if we throw a ball in the air, we've talked about this before. Oh. It takes about the same amount of time to go up. It takes the same amount of time to go up as it does to come down. So we're talking about giving it some initial velocity. It makes it to the top of its run up here someplace where the velocity is 0. And since gravity slowed it down on the way up, but then sped it up on the way down, when it comes back down here, it'll be traveling the same speed as it was on the way up, and it took the same time to go up as come down. That's not entirely accurate, even for the ball. The ball experiences air resistance in real life, and on the ramp, we have friction. The time it takes something to move is going to be dependent on the acceleration. When something accelerates fast, it takes less time than when something accelerates slow. Would you all agree with that statement? Is that easy to understand? And if I want to go from here to the back of the room, I can reduce how long it takes by accelerating at a high rate. So let's consider our problem for a moment, that as it's phrased, where I have a ramp. Okay. All right, so, and then we have a box on it. I say to you that the box has been given some kick, which means it has an initial velocity. That's the initial velocity. It's in that direction. It's going that way. Everybody okay with that? Any question about it? It's experiencing two forces then along the ramp. It's experiencing more forces than that, but the ones that control its motion on the ramp will be friction and mg sine theta. Mg sine theta will be definitely that way, down the ramp. Mg sine theta will always be down the ramp. But since the box is sliding up the ramp, friction has to oppose motion, so friction is down the ramp. Everybody good so far? So this governs the trip up the ramp. The box makes it up the ramp, and eventually that acceleration will stop it, and it'll have a velocity of 0 here. We good for the trip up? So if I wanted to know how long it would take, the net force on the way up would equal ma. On the way up, I would get minus mg sine theta minus friction equals ma. Both of them point in the same direction, creating a large amount of acceleration. On the way down, the box starts here with an initial velocity of 0 and then begins to slide back down the ramp. On its way down, it's experiencing two forces. Mg sine theta down the ramp, but friction up the ramp. Which means that the acceleration, which is causing it to go down the ramp, is going to be a smaller number than the acceleration that was causing it to stop. So it's going to take longer to come back down the ramp and be traveling slower when it gets down to the bottom. Both of those have to happen. And it's because the force of friction switches directions. On the way down, the net force will equal ma. I'm going to make down the ramp positive now. So I'll get mg sine theta minus friction equals ma. This will be a smaller number. In this case, they made the number bigger. More negative, but still a bigger number. In this case, because one is positive and one is negative, it's going to make it a smaller number. And that's why it takes longer to go down the ramp than up the ramp. You understand that I would put on here, it would take the same amount of time, which would be a very likely choice, one that you would be tricked into thinking about doing. Think about the ball question. Air resistance has to be in the opposite direction of motion. I'd even say that to you on the test. It might not be enough to convince you that it takes longer for a ball to come back down than it does to go up in real life when we have air and stuff in there. There's two things about this I would like you to know. First, you throw the phone. If you throw the phone, there's a force on the phone. At the same time, there's an equal but opposite force on you. Now, please be aware, this force only exists while you and the phone are touching. The instant you are no longer touching, that force disappears. So this acceleration only lasts while you and the phone are touching. The moment you're no longer touching, you're not pushing on the phone anymore. But the net force on the phone is the same as the net force on you. But the phone is definitely going to have a bigger acceleration because the phone is tiny compared to you. On the other hand, you will accelerate backwards. At the end of this, you will be going this way, and your phone will be going that way. Bye-bye, phone. To be in a circular path, the net force has to be unbalanced. There has to be an unbalanced force. Okay, close that conversation. It's unbalanced. I set it equal to MA. That unbalanced force must be precisely equal to that ratio, or you're not in a circular orbit. That's what I mean by these have to be matched. The forces aren't balanced. The force is balanced by the centripetal acceleration. This equation is balanced. What is it? Hey guys, shh.
The frictional force, would it be the same regardless of how
Oh yeah. Yeah, it doesn't matter how fast you're going. Friction is based on a normal force. Your motion doesn't change the normal force. At least not if it's horizontal. So if your velocity doesn't have any change to the normal force, then the frictional force stays the same no matter your speed.
It doesn't matter if it's static or kinetic, it's just going to stay.
No, it's all kinetic.
So
It can't be
kinetic is
static.
the one.
What's that?
So kinetic is the answer for this. The kinetic is the one that doesn't matter
Right.
how fast you're going.
Doesn't matter how fast
But
you're
for
going.
static, it does matter how